Good afternoon, everyone. This is Group 11's project, Brute Force on a Budget, weaponizing legacy enterprise hardware for high-performance password cracking. The idea behind this work is simple. Password cracking tools are powerful, but the systems people use to run them can be extremely expensive. Instead of relying on modern GPU clusters, we took a different approach. We asked, can older enterprise hardware still pack enough punch to handle real password cracking workloads? To explore that question, we defined a set of project objectives. Looking at project research and implementation, we first evaluated the real-world cracking efficiency of a CPU-only system versus modern GPU-based setups. Then, we built an automated CPU dehashing device using a Dell PowerEdge R815 and John the Ripper. And then finally, we integrated Tailscale VPN to enable a secure remote hash submission and retrieval. The outcomes of our project are as follows. We wanted to demonstrate how cryptographic weaknesses and outdated hashing algorithms can be exploited. Also, we wanted to highlight why insecure algorithms should no longer be used in modern systems. And finally, we wanted to represent that legacy enterprise hardware can stay highly effective for security auditing tasks.
Introduction to CPU versus GPU cracking. GPU contains thousands of small cores that work in parallel, which makes them extremely fast at testing password hashes. On simple algorithms like NTLM or MD5, a GPU can be up to 100 to 5 times faster than modern day CPUs. This makes GPUs ideal for brute force, mask, and large word tasks. However, that performance comes at a cost. GPUs often require more electricity, cooling, and dedicated drivers, which makes them more expensive to run over time because of the high power draw and heat output. In comparison, CPUs are built for complex logic and branching tasks. They perform better on modern, slow, and memory-hard algorithms such as bcrypt, script, and Argon 2, where parallel speed matters less than handling complicated computations. CPUs can run on almost any system with no special setup, and they generally use less power, making them more practical for remote or long-term cracking tasks, even though they tend to be slower. I'll be going over the methodology of password cracking and the process of it. So the first step is to identify the hash type and confirm how it was extracted, because the algorithm determines everything about the attack strategy. Once you know the hash, you can choose the right tool, usually something like Hashcat or John the Ripper, which support a wide range of formats and attack modes already encrypted on them. A smart approach starts with fast attacks such as dictionary or rule-based attacks, since many passwords are simple variations of common passwords. If those fail, move on to a mask or hybrid attack, which combine a word list with patterns to target likely behaviors such as adding numbers or symbols. Only use brute force attack when key space is small and has been narrowed down, because full brute force attacks is extremely time consuming, even with strong hardware. Throughout the process, you should check your benchmark and adjust attack settings so you're getting the best possible cracking speed without wasting time. Overall, the effective password cracking isn't just raw power, it's about using efficient strategies, choosing the right attack methods, and prioritizing the most promising options first.
Now this slide breaks down the technical architecture of how we achieved this. It isn't just about brute force, but also about how we managed our system resources. First up is the parallelization strategy. In our script, the command --fork is used. Technically, this triggers a system call that clones the main process. Because we are using an enterprise server with 32 physical cores, we couldn't just run the program once. We had to spawn 32 independent instances. This assigns a dedicated worker to every single core. Unlike a GPU, which shares resources across thousands of threads, this CPU architecture gives every worker its own dedicated cache memory. That is why the R815 is so effective at complex tasks, because it is working without resource contention. Now, second is the logic behind the attack. We utilized a rule-based mangling engine. If you look at this diagram, you can follow how it works. The CPU takes a base word like password and procedurally modifies it based on human behavior patterns such as capitalizing the first letter, adding a year like 2023, or swapping an E for a 3. Common modifications that increase the likelihood to cracking the password. Now, mathematically this works wonders. It keeps the search space small like a dictionary attack and remains very effective like a brute force attack. It is the reason why a password like password with a @ symbol and a 1 is cracked in seconds, even though it looks complex. Now, moving on to the defense against these attacks, how do we actually stop this from happening to our passwords in the real world? The answer lies in salting and iterations. The attack we built relies on speed. To defeat it, we have to make the math very expensive. By implementing salting, we add random data to the password before hashing it, which breaks pre-computed tables. But more importantly, by using work factors, this forces the CPU to hash the same password 10,000 times before checking it. We can slow down our server from guessing millions of passwords a second to just a few hundred. This validates that while hardware is a threat, the ultimate defense is better math.
Most people assume you need expensive GPU clusters, complete with an abundance of VRAM, in order to efficiently break password hashes. For our use case, we decided to go in the opposite direction. We decided to use an outdated enterprise server. Meet the Dell PowerEdge R815. This specific unit was released in November 2011. That's more than a year before the world ever saw the iPhone 5. In the world of tech, this thing is a dinosaur. But it's a dinosaur with very sharp teeth. It's a quad-socket beast, designed to hold 4 AMD Opteron processors. While the chassis supports up to 64 physical cores, for this experiment, we are utilizing 32 cores of raw parallel processing power. It has 0 GPUs, no CUDA cores, no tensor cores, just pure multi-threaded CPU grunt. Now, you might be asking, why? An RTX 4090 can churn out 300 gigahashes per second on NTLM. Why use a server from the Obama administration? The answer is efficiency per dollar. A modern GPU rig capable of high-level cracking costs upwards of $2,000 or $3,000. This R815, you can find them on eBay for almost $200. While we look at standard algorithms like MD5, sure, the GPU wins on raw speed. But when we switch to modern memory-hard hashing algorithms like bcrypt or Argon 2, the playing field changes. These algorithms were literally designed to resist GPUs. They punish the parallel architecture of a graphics card, but are surprisingly manageable for a CPU with massive memory bandwidth. So, we built the CPU dehashing device. By stripping away the bloat and running a headless Linux kernel, we can dedicate every cycle of those 32 cores to one task, dehashing. We aren't trying to beat the speed of light, we are trying to beat the speed of budget. We are proving that you don't need a defense contractor's budget to audit security. You just need to know how to repurpose the heavy iron that the industry left behind. In conclusion, the R815 proves that old hardware isn't obsolete. It's just waiting for the right engineer to give it a new mission. To prove this, we've created a demo video using a bash script we crafted to work cleanly with our tool John the Ripper.
Alright, welcome to Group 11's live demonstration. I'm going to be showing you guys how the script that we built actually works and what the realistic use case for this is. So, we have ParrotOS pulled up here. We have 2 terminals, which is the expectation that you'll be having, whether you're running this remotely via Tailscale or using the actual server itself. So, we'll be going to one of the terminals here, and I'm going to actually start it up, and all that requires is the /activator.sh command. As you can see, we have status online, cores detected 32. That is dynamic, and we have the engine path and the waiting for targets. On the left side, you can see that we have the actual list of MD5 hashes we'll be cracking here. So we have 50. The first 10 are easy to break, the second 20 are a little bit harder, and the remaining 30 are enterprise secure. So we'll see what we actually can do against this list here. So the command to actually activate it, all you have to do is move the hash file that we have into the project drop zone directory. So as you can see, it breaks all of those ones instantly, and this is not using a word list, this is with pure brute force. It doesn't even take 2 seconds to break through the first section, and the remaining are going to be brute forced as well. So we didn't actually record the entirety of it for the sake of brevity, but I will say it did take less than 3 minutes to break all of them. So even by the standards of enterprise secure passwords, a piece of hardware from 2010 can break more than 30 of them in under 3 minutes.
This slide breaks down 3 real-world scenarios where this setup becomes dangerous. First is the red team reality. Attackers don't always have access to huge cloud computing infrastructure like AWS or massive GPU clusters. A lot of the time, they rely on whatever compromised hardware they can find on the network. If they stumble upon like an old server like this R815 sitting in a closet, they can weaponize it without anyone noticing. Second is remote access. In our network, it consists of using Tailscale, which is basically a secure mesh VPN that lets all your devices talk to each other no matter where they are, without needing to set up port forwarding or any traditional VPN. This mimics a real command and control setup where an attacker could be sitting in a coffee shop, capture a hash from Wi-Fi interception, and instantly send it back to the server at home to be cracked. They don't need the heavy hardware with them, they just need that remote connection. Third is living off the land. This concept is crucial as repurposing old servers mimics how persistent threats utilize forgotten infrastructure. IT departments often ignore legacy servers because they don't think they are doing anything critical. That makes them the perfect hiding spot for running heavy cracking tasks undetected. Now, for cryptographic takeaways, what do we actually learn from cracking these MD5 hashes? Well, takeaway 1 is that MD5 is obsolete. Its biggest flaw is its speed. MD5 was designed to be fast, and that speed is exactly what makes it dangerous today. Fast hashing typically leads to fast guessing, and if your system still uses MD5, you're basically giving a head start for these attackers. Takeaway 2 is complexity isn't enough. We often tell users to make passwords complex, like admin 1234 exclamation point, having the capital letter and special character, but our results show that those so-called enterprise weak passwords just fail as fast as just 123456. Rule-based attacks can predict these patterns instantly, and complexity without the length is nothing more than a speed bump. Takeaway 3 is CPU still matters. And this is the biggest one for our project, as massively parallel CPUs are still a valid, cost-effective option for security auditing and cracking. You don't need a GPU to break weak crypto, you just need enough CPU cores working together. Thank you.